Okay, so welcome back everyone to Legion School. Today we'll be continuing talking about the high-level runtime. Sean will be back next week with his next low-level session. Okay, so last time we spent a lot of time talking about how individual tasks execute. We went through how they walk through their different stages of the pipeline, how there were additional stages for completing tasks where tasks have to wait for all their children to execute, or children to both complete and commit before they can complete and commit themselves. And we saw lots of details about how those individual tasks and points executed. Today, what I want to do is actually dig in a little bit more into how index-based tasks work, so we can actually see the process by which how we execute index-based tasks. Okay, so let's actually just start off looking at the launch call for launching an index-based task, and we'll see what happens. And then we're going to go through the pipeline and just follow the operational pipeline for a task to see how it's executed. Okay, so if we look inside of runtime.cc and we look for execute index space, it's going to be, I think it's execute index space. Yes. Here's our, I guess there are a couple of them. Some of them are old and deprecated. Here's a more recent one. There are actually two variations of this call. So the first execute index space takes a context launcher here and returns a future map, which will give you back a future map, which contains a future for every single point in the index space. And what you'll see is that there's some special logic here for handling if something has been predicated false. That's generally not going to run. In general, what we do is this part down here. We get an available index-based task object. We fill it in with all of its information. We initialize it, and then we can just put this. We actually call this execute task launch, which does some checking. But effectively, what it does is it goes and adds this index task that we created into the queue, or into the dependence queue, which is the first stage of the pipeline. Okay, now one of the interesting things about index-based tasks that I actually want to show you, let's actually jump back here to legiontasks.cc. Remember again that all of our task implementation is in legiontasks.cc. So if we search for this index task class, here it is. There's a bunch of our normal calls, activating and deactivating, initializing, filling in all the fields for index-based tasks. But the method I want to show you first is dependence analysis. See if we can find it here. Here we go, trigger dependence analysis. So this is trigger dependence analysis for index-based tasks. And one of the interesting things that you see here is that we actually perform dependence analysis across all of the points in the index-based task in one pass. And the way that we're doing this is, we're taking advantage of the fact that the region requirements for index-based tasks are upper bounds on the sets of regions that our subtasks, or that the little point tasks inside of our index-based tasks are going to use. So what this means is that because all of our region requirements here that we're iterating over, here's the loop where we perform the dependence analysis on each of our different region requirements. Because we know that each of these region requirements are upper bounds on the regions that our point tasks are going to use, we can just do a dependence analysis conservatively, saying we're going to use whatever those upper bounds are. And it will capture all the correct and necessary mapping dependencies for this index-based task, regardless of what our point tasks are actually going to end up mapping. And so what you'll see here is that we're trying to leverage the advantage of index-based tasks, of trying to amortize the cost of doing a lot of analysis for single point tasks. And instead, we're doing it over a whole bunch of them at the same time by effectively doing it over the upper bounds for this index-based task. This is an important detail for index-based tasks. What you're going to see is we're going to go as long as we can before we actually enumerate all the individual points inside of these index-based tasks. We're going to do as much as we can in our analysis, just working with these upper bounds that we've been given of region requirements for this index-based task launch. This is the first detail of index-based tasks where they sort of differ from individual point tasks, and that is that we're doing analysis over all the points at the same time by using these upper bounds. Okay, but while that's a little bit different, one of the important details is that the analysis here really just thinks of the index-based task as another operation, another node in the dynamic data flow graph that we're computing, and so we get dependencies, mapping dependencies, and so forth on other operations exactly the same way that we do with all the other kinds of operations and individual tasks that we've seen dependence analysis for in the past. So really, when we compute data dependencies, they're all just on this whole index-based task object. So we're gonna, when it's actually time for us to map this index-based task, we're gonna map the whole thing all at once and not do individual point tasks all individually. Okay, so that's the dependence analysis phase for index-based tasks. It'll operate just like another operation. Eventually, at some point, all of its mapping dependencies will be satisfied. It will go into the. We can actually look at. I think it's going to be trigger mapping here. Right, it's not going to have a trigger mapping call because it's a predicated operation. So there's a. Let's see. What was the name of the call that the speculative op? Let's see if I can remember. The speculative op actually uses. Notify it when it's ready to map. We'll see if I can find it here. If not, we will just move on and I'll tell you what happens. There's result true. Right, so I'm forgetting here, but effectively the index-based task is a predicated operation. So it goes through the speculative, it inherits from speculative op through the task op class. And so when it's ready to map and its speculation has been resolved, we'll actually put it into the mapping queue of tasks that are ready to map inside the mappers, inside the processor managers that we talked about in the past. At some point, that mapper will decide to actually map this index-based task, at which point it will call trigger execution. So let's actually look at trigger execution in here. Right, and here's trigger execution. I guess it's for a single task. I guess what I want is actually trigger execution for multitasks. Because an index-based task actually inherits from multitasks. If you remember from our I guess 2 lessons ago, we looked at the type hierarchy, and so multitasks inherit from task ops, and then index-based tasks inherit from multitasks. So when this task is actually ready to execute and actually be mapped and run, we get this trigger execution call that comes in from after the mapper has said we're ready to map this task. Now you recall I guess 2 times ago, one of the things we looked at is we actually looked at trigger execution for individual tasks or single tasks. And it was a little bit more simple than this, but it had a very similar structure. So actually, if I just to refresh your memory, here's the single task call, here's the trigger execution call that we looked at for single task. And you saw, remember, there are 2 different branches, one for if we're remote and one for not. And you remember that we have to do things like check for pre-mapping, check whether or not we're going to already map this task or whether we're going to distribute it and perform mapping and launch the task and so forth. So there's a whole bunch of calls here for actually doing different operations on this task. So what I want to do now is actually dig into the implementation of trigger execution for multitasks to actually show you a little bit how they operate and how they're a little bit different. They have an extra stage that makes things a little bit more complicated than what you normally get inside of the individual tasks that we were looking at the last time. Okay, so again, we're going to have a little branch here, checking to see whether or not we're remote or not. Let's actually skip the remote case first. We'll come back to it. Okay, so if we're in this else branch, we're actually looking to see if it's not remote. So the first thing we obviously have to do is we have to check to see if this task has been pre-mapped. If it has, we're already good, and we can go into this if. If not, we actually need to execute the pre-map task call to actually do the pre-mapping. The pre-mapping involves traversing each of the region requirements from where the parent task had privileges down to where this task is requesting privileges. One detail is that the index-based tasks, we only do this traversal down to the upper bounds named by the region requirements. We don't actually go to each of the individual points. We'll actually handle that when we go to actually map the point tasks. They'll walk from where those are down to each of their individually requested region requirements. And we'll show you how that works probably in a later lecture. Okay, if we fail this, if we actually failed to pre-map our task, you'll notice down here there's an else statement which will set success to false, indicating that we failed to pre-map. In the new version of the runtime that we just pushed out a little while ago, it's pretty much impossible to pre-map or to fail pre-mapping now. But it's still important to check just in case. Pretty much all of these calls are designed to be able to fail at some point. So our next statement here is whether or not we're going to be locally mapped. So remember, the mapper can decide whether or not we're going to map this task locally on the current processor where the task was created, or whether we're going to map it remotely where the task is actually being sent. And this actually has a very particular meaning for index-based tasks. So an individual task, it's very easy to think of mapping on the local processor or mapping on the remote processor. If we actually choose to map an index space locally on the processor where the index-based task was launched, one of the things we have to do is we actually have to enumerate all those points inside the index-based task and then actually run the task. Otherwise, what we're going to do is actually going to try to avoid enumerating all the points until we actually need to map all those point tasks. So let's actually do the non-locally mapped case first, and then we'll come back to this to locally mapped case. Okay, so here's the else statement for non-locally mapped. So you see it's pretty simple. If we're not mapping locally, the first thing we're going to do is check to see if we want to distribute this task. The mapper may have requested that we actually send this task to another processor somewhere. And there are two cases for how we actually send this task to another processor. And that is the first case has to do with with the extra stage that occurs for index-based tasks. So what we're going to see is that index-based tasks have an extra stage pipeline, which is called slicing. And the idea behind slicing is that we actually want to have ways for the mappers to control how these index-based tasks get broken up into chunks and moved around the machine. It's likely that you don't actually want to send the whole index-based task to a single processor somewhere in the machine. It's much more common that what we do is we end up breaking up these point tasks into subsets and then sending little groups of them to different processors all around the machine. And so in order to do this, we have an extra stage in this index-based task execution called slicing. And so what we're going to do is we're going to first check here to see if we're already sliced. If we're already sliced, then we can do this map and launch phase, which is okay. Sorry, I may have confused you a little bit here. This distribute task will actually send the tasks to a remote node, and it only returns true if we're staying local to the current node. So distribute actually may involve sending this task away to a remote node. We'll actually look at this in just a minute. But then down here, if we are still local, there are two phases to our pipeline that we may have to do. So if we're already sliced, effectively, if the mapper has already broken us up into chunks, and we'll see how that's going to happen when we look at this slice index-based call. But if we've already done that, then we can actually go ahead and map and launch this set of tasks, point tasks that we have here locally. We'll actually come back and we'll actually go and look at map and launch a little later today. Alternatively, what we can do is we actually can call slice index-based task, which is actually going to invoke the mapper and ask the mapper to actually take this index space of tasks and break it up into a bunch of into different subsets, which we call slices of the index space of points. And then we'll create separate slice task objects and then run them through this pipeline as well. Okay, let's actually take a minute to actually dive into some of these methods in a little more detail so you can actually see what's going on. We'll dig into them, and then we'll come back here and we'll look at some of these other cases, like the locally mapped case and the remote case. Okay, so let's look at distribute task first. Let's see here. There we go. Distribute task. There's a special case here checking to see that we're not going to be in here locally mapped. We should never get this call in an index-based task if we're going to be locally mapped. So what you'll see, the first thing that we do is in this case where we actually want to send this index-based task to a remote node, one of the things that we do is we actually we're going to clone this index-based task as a slice task object. Now, this is going to be an important invariant of the high-level runtime, which is that index-based task objects never leave the node that they're on. Effectively, once they're created, they're always going to stay on that node. Now, what we're going to do is we're actually going to the only sets of multitasks that can actually move around remotely are these slice task objects here. Sliced tasks, if you recall from an earlier lecture, are another kind of task object. They also inherit from the multitask class, so they have a lot of similarities to the index-based tasks. Effectively, they have a lot of shared infrastructure in the abstract multitask abstract class. So they share some similarities, but they have a little bit of difference. And one of the differences is that they're ones that can actually be packed up and sent remotely to remote nodes. So you can think of effectively as slice tasks as being the kind of task that we can move around inside the machine, that the mapper can actually control as part of its movement. So in order to actually send this this index-based task around, what we do is we actually create a slice task. Now, slice task can represent any subset of the index base of tasks that an initial index-based task could have originally represented. So in this case, we're creating a slice task, which actually is going to own all of the points inside of this index base. We're passing in this index domain here that you can see. And that's what allows us to say that we're actually going to pass around all the points initially with this slice task. And what you do is you see we call this this runtime send task method that we had before. And then, of course, the slice task knows how to pack itself up and serialize itself so it can be sent to a remote node. So we looked at send task before, so I'm not going to dig into that today. You can actually follow this through and see how it gets packed and unpacked, but it's very, very similar to how individual tasks get packed and sent and unpacked. So what we've done here is we've effectively cloned this index-based task object as a slice task object, and then we've sent it to a remote node to actually have itself unpack there and then progress through the same multitask trigger execution pipeline that the index-based task is going through that we were just looking at. Okay, so that's distribute task. Let's actually jump back. Let's look at the next call that was in here. We're in trigger execution for multitask. So scrolling back down here. Okay, let's actually handle the case where so let's say that we've done our distribute task, and we actually said we wanted to stay on the local node, in which case this returned true, so we're still local to this node. And let's say that we haven't sliced yet. Let's actually do the slicing stage next, which is the way most of these index-based tasks actually execute. What you'll see is we have this separate call here called slice index base, which is actually going to go through and perform the slicing operation for this index-based task. Let's actually search for slice index base. You'll notice again that this is another method on the multitask class, which means that it's the same for both index-based tasks and slice task objects. So no matter which kind of object we're going to go through the same routine to actually slice this index base into chunks. Okay, there's a bunch of logging here at the top. I'm going to skip that. You see, the first thing we're going to do is we're going to mark slice to true, indicating that we're going to be slicing this task. Once we've actually sliced this object, we can't actually steal it. Effectively, we can still make the pieces that we're slicing stealable, but we can't actually steal this task anymore. What we're going to do is we're going to invoke the mapper to actually perform the slicing operation. So there's a mapper call called slice domain, where we give it the domain for this current set of points that we own. And what the mapper comes back with are the set of what we call domain splits. And you'll see that this is actually, the type of domain split is actually defined in the mapper class. And it's actually, just to show you what it looks like, so you can see the fields on here, just to make this concrete. Let's actually look in the mapper class. I'm in legion.h header file, looking at mapper. You can see here's the domain split struct. It's pretty simple. It has 4 fields. You can give it a domain, which is a new subset of the points. You can assign a processor, which is where you want that set of points to be sent. You can set this recurse flag, which says whether or not you want to invoke domain split on this slice that you just created on the processor where you send this slice to. This allows you to do hierarchical decomposition and slicing of index-based tasks. And then you can mark whether or not you want this slice to be stealable. And just to show you the mapper call itself, just look at serve slice domain. Here's the actual mapper call itself. We give you a task, we give you a domain to slice, and we expect you to fill in this set of domain splits, or a set of slices containing domain splits, naming different subsets of points that you actually want to be broken up into new slice tasks and sent to remote processors around the machine. Okay, let's jump back to legion tasks.cc. We were looking at slice index base. Okay, so this mapper call goes and invokes the mapper for this task, actually asking it to slice up this index-based task into slices. And what we do is when we come back, we get a set of splits that we're supposed to handle. We check to see if the splits are empty. If they are, we can say the mapper has done something wrong. At this point, we can, give them a little error message about doing something bad. If it succeeded, what we've got is a whole bunch of splits that we want to then create new slice tasks for. Okay, so what we do is we're going to iterate over all of these splits. What we're doing here is actually doing a little check here to actually make sure that the volume of the splits that the mapper has specified is actually adding up to the volume of the original index space domain. You'll notice here that this is all wrapped in a debug because this analysis can be a little bit expensive. So there's a lot of logic here for checking to make sure that the mapper has given us a volume of effectively all the points in the original index space that we passed in are again represented in this new set of splits that the mapper has requested. So this is a big if-def, and you see we have different cases for different dimensions of index spaces, whether we have unstructured or any one of a structured dimension. But that if-def ends right here. So that's all just checking of the mapper code. The mapper has done a good thing. But if we've succeeded to pass all that, one of the things that we do is, again, we call this clone as slice task operation. And you'll notice that if we actually look at this clone as slice task operation, what you'll see is that this is a operation on, it's a virtual method on the multitask object. And what it does is it's going to clone all the fields of our current task and give us back a new slice task. But we're going to give it a slightly different domain containing, all of the information about the new domain that this is going to represent, the processor we're going to send this to, whether or not we should recursively invoke slice. So this is effectively saying whether or not the new slice that we're creating has already been sliced or not, this recurse field set by the mapper. And then also saying whether or not it's stealable and so forth. Okay, just to show you briefly this clone as slice task. There's two variations of it. It's a virtual method. So we can have one. We have one that's defined on index-based tasks. We know how to clone those as an index-based task. What you'll see is that there's some methods here that dive down, but we're just cloning all the necessary fields from our current object into this new slice task object, so that it has all the necessary information to actually execute all the point tasks that it needs. But this is all just a bunch of copying. There's nothing really intelligent going on here. And similarly, you'll see there's another clone as slice task. So we can actually clone a current slice task as a new slice task with a new domain to actually create a new subset of the points that we're supposed to be mapping. And again, this is all just copying. There's no magic going on here. So back to slice index space. Okay, so once we've cloned our task as a new slice task object and given it a new subset of the domain that our mapper has requested, at this point we can add it to our set of slices, and we record that this is a set of slices that we need to wait for in order to be mapped, in order to consider ourselves mapped. And then once we've done that, we have this new data structure called slices, which contains all the sub-slices that we've generated as part of our slicing stage of the pipeline. Just to show you where that data structure is declared so you can be familiar with it, if we actually look in legion tasks.h and we search for the multitask class, remember that both index-based tasks and slice tasks inherit from this multitask class. There's a whole bunch of virtual methods. There's only a few data structures or member fields here for this multitask, but one of them here is this standard list of slice tasks, which actually allow you to know the set of slices that we've generated as a part of this this task execution. Okay, jumping back to legion task.cc, coming back to slice index space. Okay. All right, so once we finish slicing, I guess that's the end of this phase of the pipeline. One of the things that we actually, okay, so let's pop back out of index-based slice. Let's jump back to trigger execution for multitasks. I thought here, actually, I'm getting myself a little tangled up here. I apologize. I'm trying to remember what happens after we've actually sliced all these tasks. So I believe that we're actually supposed to do something with these slices that we've generated. I'm trying to remember exactly how that works. Make sure I didn't miss anything. I apologize. Some of this code has been written a long, long time ago. Okay. Well, let's just work our way through things here. Okay, so I guess what actually ends up happening here, sorry, I'm in the wrong trigger execution. So once we've sliced our index-based task, we've actually broken up our index-based task into individual slices. And I believe what actually ends up happening here, actually, I actually want to track this down and make sure that I am remembering exactly how this works. But I believe that what happens is after we call slice index-based task, or slice index-base, what should actually happen is we should actually end up putting each of these slice tasks that we generated into the pipeline so that they can actually go and execute themselves through this trigger execution.
Are you looking for trigger slices?
Yeah, where is that?
Cool success equals trigger slices, about 5 lines down from your mouse.
Ah, there's what I was looking for. Thank you very much, Elliot. That is exactly the call that I was looking for. I was thinking to myself that we haven't, actually done anything with these slices and that we should actually be doing something with them. And yes, thank you, Elliot. This is exactly the call that we should be looking for. So after we've generated all of our slices, we can actually trigger them, which means that they're effectively ready to execute. And you'll notice that we won't actually have to do the dependence analysis for all these slices. Effectively, we already know that they're safe to map and everything because our whole index-based task is ready to map. So yes, this is exactly the call that I was looking for. Let's actually look into trigger slices here. What you'll see here is that trigger slices actually does a thing called deferred slicing, which is actually, this is an slightly expensive operation, so we might want to offload it onto another utility processor. So in some cases, we might actually have multiple utility processors running. We don't want to actually block up, possibly triggering all these different slices by doing them one in a row on this one utility processor. We have this deferred slicer object, which is actually going to trigger all the different slice objects that we made in parallel. We can actually look at this real quick. This deferred slicer is really pretty simple. What you'll see is what it actually does is it really just takes all these slice tasks, this list of slices that we've generated, and we launch a new utility or new meta task. Again, here's this HLR underscore something ID, and we're using the high-level runtime meta task to spawn this onto another utility processor. And what we're doing is we're just dumping all of these different slices onto the utility processor and having it call trigger execution these various slices, and then we're just waiting for the slices to finish mapping and checking to make sure they all succeeded. Okay, so what this, I'm not going to dig in this. You can actually track through this yourself, but the end result is that each of these different slices that we've generated have trigger execution invoked on them. So let's jump back to trigger execution for multitasks. So again, remember that slice tasks are a kind of multitask. So once we've made new slices, we actually just run them right through the same pipeline that our index-based task was running through before. Again, let's skip the remote case. We'll skip the locally mapped case. But again, you can see these slices now come back through the same part of the pipeline that we were looking at before. So again, we'll see, if distribute task, if the mapper asks us to send this slice to a new remote processor, we can actually go and pack up that slice task and distribute it. So in this case, we end up calling the slice task version of distribute task. So distribute task is a virtual method, and there's a slice task version, which doesn't need to clone itself because we already know that we can send slices remotely. We can check to see if the mapper asked us to be recursively sliced or not. And this is again if we're local. If we're remote, there's going to be a different case. But again, we can check to see if the mapper asked us to stay local or not. Or if we are local, we can check to see if the mapper asked for us to be recursively sliced, in which case we can go back through the slice index space call again. And again, the same thing happens. We can generate new subslices, and the mapper can continue breaking up our index space into smaller and smaller chunks of points. Alternatively, if we're not sliced, then we can just go ahead and call, if we are already sliced, we can go ahead and just call this this map and launch task, which is what I want to look at next. But there's an important, before I do, I just want to reiterate this point that this pipeline here of operations that we're seeing for this trigger execution for this multitasker is being run both by index-based task objects and slice task objects. And it's sufficient to capture all the different cases that we might need to incur. And there's a lot of similarities between how the index-based task objects and these slice task objects traverse this pipeline. Okay, let's actually go look at map and launch next. And then what we'll do is we'll come back here and actually go through some of these other cases that are going on inside this trigger execution call. Okay, so let's look at map and launch here. Okay, in this case, the map and launch, there are two versions of map and launch. Again, it's a virtual method on multitasks. So there's one for index-based tasks and there's one for slice tasks. One of the things that we'll see is that the index-based task one will only ever be invoked if we actually had slices which failed to map when they were running. In which case we will get invoked again to trigger execution. We'll come back in here to call map and launch. In which case all we need to do is re-trigger the slices that fail to map. And so there's a couple of instructions here checking some stuff, but really all it's saying is, we had some slices that failed to map, so trigger them again, and they'll go off and map themselves and launch themselves. But the map and launch for slice task is where actually all the real work gets done. Okay, so map and launch for a slice task. What we're going to do is when we know we're ready to actually map this slice task, what we want to do is actually go through and enumerate all the different points inside of the index-based domain that this slice task owns. We're going to create a separate point task for every one of those, for every one of our points that we own. And then we're going to go through and request that each one of those point tasks get mapped. If they all map, then we're ready to launch all our points. Otherwise, we're going to move on. Okay. So the first thing we're going to do is we haven't already enumerated our points in our slice task. Again, remember that we may already have, enumerated them all, but we may have failed to map, and therefore we can come back through this path. So this is just a check to see if we actually need to do the enumeration. We'll go look at enumerate points in just a minute. It's going to have a familiar structure to it. Once we've enumerated all our points, what we're going to do is we're going to have filled in this, what we call the local points. What we're going to fill in is we're actually going to have this vector of points, point task objects that we've actually filled in. Let's actually go look at enumerate points so we can actually see what it does. So we look at enumerate points. Notice this is a method only on a slice task. We actually do a little mapper call here to ask the mapper to pick a variant for all of our point tasks to use. That's just a little detail at the moment. But one of the things we're going to do is we're going to create, the main thing that we're going to do here is enumerate all of our points. So we're going to iterate over all of our points in our index in our domain. And then what we're going to do is we're going to clone this slice task as a point task. So you remember again that we had this clone as slice task method, which we had for cloning both index-based tasks and slice tasks as new slice tasks for different domain sizes and so forth. And what we do is we have this other method here called clone as point task, which is actually going to be the method which actually clones this slice task as a point task object. So that just creates a new point task and then copies over all the fields from the slice task object that are necessary for actually executing this point task object. And again, there's no magic there. There's just copying of fields, making sure everything is consistent. And then what we do is we add to this points data structure, which is just a doubly ended queue of all of the point task objects that are associated with this slice. And remember that we're needing to check that in order to make sure that we can't be considered mapped ourselves until all of our children have mapped. So we're checking all of that information by keeping a track of when all of our points have considered themselves mapped. So we're doing some event chaining here. And the other thing that slice task tracker, they track to make sure that actually track to see which point tasks are in different phases of the execution. So that's where we're storing information about, which points are unmapped, which ones are incomplete, and which ones are uncommitted. Okay, so this enumerate points task is really pretty simple. Let's jump back to map and launch for index space or for slice tasks. So once again, here's the check on this doubly indent queue to see if it's empty or not, which is our indication whether or not we've actually enumerated our points. At some point, we've actually enumerated all our points. At this point, we're actually ready to try and map all of these different points. Okay, so what we do, we actually make a little copy of this vector. There's an interesting race condition here that can occur, and there's a reason that we're making this copy, and that is that one of the things that can happen is that once we've actually called a launch task on the very last point task, it can actually result in that task running and then cleaning up this slice task before we've actually exited this function call, which can invalidate a bunch of information, like, for example, the size of this points.size data structure. So effectively, we need to have copied any data that we need. Effectively, after we do the very last one of these launch calls, we might end up being cleaned up ourselves. We need to have any local data that we need on the stack. So we're actually copying a little bit of information. Normally, we're actually copying this whole set of points from our vector. But what we do is we keep a track of this what we call mapping index, which says which tasks have been successfully mapped and launched onto the low-level runtime. And so if we end up, failing a mapping and having to restart at a later point in time, we know the index from where we had to restart from. That's what this mapping index is tracking here. Okay, so what we do is we fast forward through any points which we've already mapped and launched. And then what we do is we're going to iterate over all these local points copied into this data structure on our stack and actually try to map and launch them. So what we do is we end up calling point task error perform mapping. And it turns out that we actually looked at where this goes previously. Let me just show you so you can make the connection. But if we look at point task perform mapping, what you'll see is that this is a very simple call, and it ends up calling this map all regions call that we looked at, I guess it's only one lecture ago. This map all regions is responsible for mapping all of the region requirements for this task and saying whether or not we succeeded. And so what you see is that we're really just falling back onto that the same infrastructure that we already have for mapping and executing individual tasks that we already looked at for individual tasks the previous time. Okay, so back to slice task. We were looking at what was it? Map and launch. That's right. Okay, so this perform mapping call is just falling back onto the same infrastructure that we already have for individual point tasks or single tasks. We check to see if we succeeded. If we succeeded to map, then we can get to skip this bad case. I guess if we failed to map, we'd set map success to false, and we would break. And importantly, what we're doing is we're actually remembering the mapping index of the last point that we created, or last point that we successfully mapped. So that when we have to restart, we know where to restart from. If we did succeed, though, we can then call a launch task, which actually we again looked at that last week also. That just calls the launch task method on a single task object. So again, recall that point task objects are actually a subtype of single task objects. So when we call a launch task, that's just going and launching that task onto an actual low-level processor on the actual machine. And again, once we call this call the last one of our points, it may be that all the point tasks actually end up running and then telling us to clean up ourselves. It seems like an unlikely race, but I have actually seen it happen in practice, which is why we pulled a bunch of extra stuff onto our stack to make sure that we don't end up cleaning ourselves up and still referencing data structures from an old version of this slice task object. Okay, there's a special case here for must parallelism. I'm going to skip that for today. But what we do is we return whether or not we successfully mapped and launched all of our various point tasks. So that's what map and launch does for slice tasks. It literally generates all of the point tasks, maps them onto their processors, and then kicks them off on those processors. Okay, now let's pop the stack and jump back into trigger executions so we can actually look at some of these other cases in this trigger execution method. Okay, so we've done a very small part of it. We've done this part down here, this part where we've successfully pre-mapped, and then we've not been locally mapped, so we've been able to distribute ourselves. And if we stayed local, we know how to perform our mapping and then launch our task. Or sorry, this is the wrong version. I'm sorry about that. We actually want this multitask version. So we know that if we we know how to distribute ourselves. We know that if we stayed local, we check to see if we sliced. If we sliced, we can map and launch. If not, we call slice index base, which then invokes the same trigger execution method, generates new slices, and then calls trigger execution on each of those slices to traverse the same pipeline. Okay, let's actually do the remote case first before we handle the locally mapped case. The locally mapped case is a little bit interesting, so I want to do that separately. But let's say we actually called this distribute task on a slice task object. So you can see if we have slice task, distribute task, what we do is we check to see if this is our current processor. If the mapper is said to send us to another processor, our target processor is different than our current processor, we call runtime task. And that will pack up this slice task and send it to a remote node, at which point it will be unpacked on that remote node and trigger execution will be invoked on that slice task object. In which case we find ourselves right back in multitask trigger execution. This time, in the case we got sent remotely, this is remote case will be true. Okay, so if we come into this is remote case, what we want to do is to see, first off, check to see if the mapper has actually changed anything to actually distribute us again. It's possible that we may have actually been decided to be sent somewhere else. But in most cases, we're probably still going to be local. So if we're still local on this remote node that we're on, the first thing we're going to do is check to see if if the mapper has requested that we should be sliced again. So in this case, this would be the example of the case where we made a slice task, but the mapper asked us to recursively invoke the slice domain operation on this slice. And so if sliced is false because the mapper asked us to do the recursive invocation of slice domain, we're going to come right back in here and call slice index base again. And so as you remember, what that does is it invokes the mapper to call slice domain. It generates a whole bunch of new slice tasks, and then we call trigger slice on those, and then they go through and run through the pipeline again themselves, which may involve those actually getting sent again to remote processors and so forth. And that's how mappers can hierarchically decompose an index space task of points into different subsets and do this recursively to possibly fan out across the machine in a more efficient manner. Okay, if isSliced is false. If isSliced is true because the mapper didn't request us to actually do the slicing, in that case it's really simple. So if sliced is true, we'll skip the is locally mapped case, and in this case we're on the node where we want to map and launch this set of slice tasks or the slice task of points. In which case we can just go ahead and call map and launch on this slice task object, which as we saw just all it does is it enumerates all the point tasks for this slice task and then maps and launches each of those point tasks individually. And so that's in this case, it's almost identical to what happens if we had stayed on the local node. So the remote mapping case is very, very simple and pretty straightforward to handle. Let's actually take a look now with the remaining time that we have left today to actually look at the locally mapped case. And this one is going to be slightly more complicated. Okay, so if you recall the locally mapped case, in this case what the mapper has asked us to do is to actually map all of the point tasks for the slice task on the local node before we actually distribute them out to a bunch of remote nodes to actually execute them. Okay, so let's start on the local node. Again, all this has to happen after we've pre-mapped. But the mapper now has asked us to actually locally map this task. Okay, so the first thing that will happen is we'll call isSliced. If we start off with the index-based task object, we know we haven't sliced yet. So we're going to end up doing is call this slice index-based task, which will actually ask the mapper to call slice domain and break up all of our different slice tasks. One important detail here is that what actually ends up happening is that you'll notice is that we generate all of our different slices, and then we call trigger execution on each of those. Again, we will have set the locally mapped or map local flag on each of those different slices. So when they come back through this trigger execution pipeline here, what will end up happening is they'll already have been pre-mapped. They will have record themselves locally mapped, and then they'll come back to this isSlice call. And if the mapper has actually asked us to recursively slice these objects, it can still do that. The thing that you'll notice is that it's actually recursively happening on the local node. So instead of fanning out, and this is why we do the slice task call here before we actually do the distribution, you'll notice the distribution call is actually in here after we've already finished slicing. And the reason for that is we actually need to enumerate all of the different slices here locally on this local node and map them here locally before we can actually send them away remotely. So we've effectively permuted the order of two of the stages of the pipeline here. Effectively, we're whereas in the remote case, we used to distribute and then slice. Now what we're doing is we're actually slicing and then distributing. And that's necessary in order to correctly handle this mapper's request to locally map all of the point tasks for this index-based task on this local node. Okay, so what you can see is you can end up recursively calling slice index base and generating more and more slices for this index base of tasks. At some point, though, the mapper will say that it's done. And what we'll do is we'll get a whole bunch of slices that come through this call and say isSliced is true. And at this point, we can actually come through here. I'm going to skip the must epic stuff here. But in most cases, what we're going to do is we're going to actually try and actually do the mapping for our slice task. So the first thing that we want to do is we want to check to see if we're actually mapping onto our local processor somewhere here on this machine, or whether we're actually going to end up sending this task away to a local or to a remote processor. So if it's our local processor, what we can do is we actually just want to, this is the case where we're not local. So this is a processor which we know we actually need to map here locally, but send the slice task away. In which case we can just call the perform mapping call, which is going to try to map all of the regions for all of the different point tasks inside of the slice. We're actually going to go look at this in a minute because it's a little bit different than the map and launch call. Effectively, we just want to do the mapping part, not do the launching part, because we know we're going to end up sending this slice task remotely. So we check to see if we can map all of our points inside of our slice. If we succeed at doing this, we can distribute our task, which actually ends up sending that slice task to whatever target processor it was initially sent to go to. Otherwise, we know it's going to stay on one of our local processors, so this distribute call might just send it to another one of our remote processors. But if it stays local, then we can just call map and launch like we did before, which will end up mapping and launching that slice task onto the local processor. Okay, the important part here is this perform mapping call. So let's actually look at perform mapping for slice tasks and index-based tasks. You notice that there's a bunch of different variants of this. Index-based tasks only get perform mapping called if they had slices that failed to map, and they need to try to remap them. But the interesting one that actually does a lot of the heavy lifting here is this slice task perform mapping. So first off, we check to see if we have our own slices, which may have actually have failed to map themselves, in which case we're going to try to remap these slices. So you see again us calling trigger execution on each of our sub slices in the case that we had been recursively sliced. Otherwise, if we don't have any slices, what we actually need to do is try to map and launch each of our different point tasks. So again, we first check to see if our points, if we've actually enumerated all our points. If we haven't, we go ahead and call enumerate points to generate all our point tasks. And then what we do is we call perform mapping on all of our different point task objects and see if they succeed. And again, this is just mapping the regions, not actually trying to execute or to launch this task launch this slice because we're most likely going to end up sending it remotely. If at any point we fail to map, we actually have to unmap all of the regions for all of the points that we've mapped so far. It's because we want to avoid resource deadlocks where we're actually holding on to physical instances in memories where we're not actually going to be able to make forward progress because we haven't actually launched the tasks. So we avoid doing that by unmapping. If we fail to map any point tasks, we unmap all the regions for all the point tasks that we had mapped before. But then if we succeed, then we can actually return success or return map success as true. At which point we'll actually be able to send this slice task to the processor where it's actually supposed to be launched and actually run it. So let's actually jump back to trigger execution here. So we were down here. If we succeeded in mapping, we can call distribute task. What that will do is pack up this slice task. The slice task objects are smart enough to know that they've enumerated all their points. They also need to pack up all their point task objects and send those remotely as well. And they're smart enough to do that. I'm not going to show you the logic for actually doing that, but it's really just a bunch of packing up and point tasks and then unpacking on remote nodes. And then what happens is when that slice task with all of its point tasks get unpacked on the remote node, then we know that we're actually ready to launch this slice task on the remote node. So in the remote case, remember we unpack everything, we call trigger execution, and what ends up happening is we'll come into this isRemote case, we'll do the distribute call, it'll still be local because we know we get sent directly to the processor where we want to run to. Then we'll come into this isLocallyMap call, and we'll know that we are locally mapped, in which case we know that we already mapped on our owner node, the node we created. In which case, all we need to do is launch off all the different point tasks for all of the different points inside of our slice. So if we look at launch task, it's a single task variant. The index-based task variant should never be called. And then the slice task version, what you'll see is that all it does is iterate over all of the point task objects that it has. And then what it does is it calls launch task on each of these different point task objects, which allows them to actually kick off and actually start running on the processor where they were mapped on this remote processor where we mapped them to. Okay, let's jump back to trigger execution and see if there's anything that we missed. So I think we've handled all the cases. So we've handled both locally mapped and remotely mapped cases. We've handled how we break up index-based tasks into slice tasks, and then how slice tasks enumerate all their point tasks to actually generate individual point tasks. And then point tasks are a subtype of single task, and we looked at how single task objects get mapped and launched and run yesterday, or I guess the last time. I guess in the last couple of minutes that I have here, I want to talk about how slice tasks actually do the completion of each of their different tasks. So if you remember last week, one of the things that we looked at is we looked at individual tasks doing trigger task complete, which was the method that got called once all of the point tasks, or once this task had finished completing, as well as all of its child tasks had actually completed as well. And we looked at this for individual tasks, but we didn't look at it for point tasks. So one of the important details of point tasks So one of the things that happens is in order to clean up an index-based task launch, we have, again, a hierarchical structure where effectively slice tasks can't be considered complete until all their point tasks are considered complete. And similarly, index-based tasks can't be considered complete until point tasks consider themselves complete. So we're looking here at point task trigger task complete, and there's another method here, trigger task commit, which actually does something similar, or which is the next stage in the pipeline. And what you see is that each of one of these point tasks have a pointer to their slice task owner, always guaranteed to be on the same node as them. And what they do is when they're actually complete, what they do is they pass back a whole bunch of information back to the slice task objects, returning information about which children have been mapped, We return privilege information about regions that were created. We record that this child task is now complete. And what you'll see is that there's a hierarchical aspect to this where the slice tasks are only allowed to consider themselves complete when they know that all of their point tasks that they've created are complete. So if you look, for example, at slice task record child complete, which is right here, what you see is that we're tracking how many incomplete points we actually have, and therefore how many other points we need to wait for before we consider ourselves complete this for this particular slice task. And then once this slice task has actually triggered everything, slice tasks also have a trigger task complete method. Then we can do we actually can call trigger slice complete. What this does is it then checks to see whether or not we can pass back information to what we call our index owner, which is a pointer to the index task object which created us. And so you see, if we're remote, we actually have to send that message back, or send all the information back in the form of a message. But if we're local, if we're on the same node as our index task owner, we can just pass everything back directly and then call complete operation on ourselves. And one important detail here that's maybe is just since we talk so much about recursively slicing index-based tasks into slices and further recursively refining them, one thing that happens is that if we've done like a hierarchical decomposition of our index space into slice tasks, so we've generated a whole bunch of different, we sliced maybe multiple times for individual slices. One thing that happens is we actually have a flat return process, whereas the intermediate slices that actually just generated new slices end up getting thrown away. And it's only the least slices that actually generate their own point tasks that actually end up returning information back to the index task owner. So we don't have to go back up the hierarchy that we generated as part of our execution. We can actually go directly back to our index task owner on whatever node we were generated on, which removes some unnecessary latency in our execution. Okay, so that was a lot of details. I think I'll probably have to cover some more of them again, just that we covered here at the end, just to clean them up a little bit, talking about how slice tasks actually end up triggering, walking through the pipeline themselves in a little more detail next time. But I think we're out of time for today. So with that, I'm going to stop. If anyone has any questions, you can ask them now or post or send questions over the email list, and we'll be happy to answer them.